Okay, in number 5, we are asked to use the rational zero theorem to list all of the possible rational zeros of this polynomial function. So this one's going to be really very, very simple and quick problem. Because remember what the possible rational zeros are? Factors of 12 over factors of negative 2. And we're going to be doing plus or minus. So we could say that it's, plus or minus. This is not my final answer, but I'm just working on this. Remember, eventually I'm going to put a plus or minus. The factors of 12 are 1, 2, 3, and 4, 6, and 12, over 1 and 2. So I'm going to go ahead and write my final answer as all of these numbers over 1, and then all of those numbers over 2. So we'll get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Now I need to repeat that, only put 2 over each one of them. So plus or minus 1/2, 1 over 2. But plus or minus 2 over 2 is plus or minus 1, and we already have that one. So plus or minus 3 over 2. Okay, plus or minus 4 over 2 is just plus or minus 2. We already have 4 over 2. 6 over 2 is 3. We already have it. 12 over 2 is 6. We already have it. So here's our complete list of possible rational zeros. All right, now a different type of problem. Number 6. Solve this polynomial inequality. If that were an equal sign, all we'd have to do is plug it into the quadratic formula or factor this to find out what the two numbers are that would give us a 0. But this is saying solve the inequality. It's a greater than 0. All right, so we'll write the answer in interval notation, and we'll graph it on this real line right here. So the first thing we do is find the boundary points, which would be if we make this an equal 0. The boundary points come from x squared plus 2x minus 48 equals 0. Let's see if we can factor that. What do we get? X has to be a plus and a minus to multiply to negative and add to a positive, and they're going to be 2 apart. At least the magnitude of the numbers will be 2 apart. We're going to have an 8 and a 6, and the 8's going to be positive, and then the 6 will be the negative. That's the factored form. So set those equal to 0, and the two boundary points will be negative 8 and positive 6. And notice I put open circles. There's a hole in the graph at negative 8 and positive 6. Because if you plug in either one of those, you're going to get 0 on the right-hand side. 0 is not greater than 0. So now that we've broken the real line up into 3 sections using these two boundary points, here, here, and here would be the 3 sections. Let's choose 3 test points. Test points will be negative 9. You could choose anything to the left of negative 8. I'll choose 0 because it's in the middle section. And I'll choose one more than 6 to get 7. These are going to be my test points. And what I want to know is what's the value of the function. And by the way, I didn't say this, but the function is the left-hand side of the inequality. So this is what I'm calling f of x. This part that I have underlined. All right, so f of 0 is negative 48. That's an easy one to plug in. If I want to plug in a negative 9, I think I'm going to plug it into this, because this is the factored form of f of x. If I plug in a negative 9, I'll get negative 9 plus 8, which is a negative 1. And a negative 9 minus 6 is negative 15, which is a positive 15. All I care about is it's greater than 0. Okay, and then f of 7 would be, if I plug it in here, I'm going to get x plus 8. 7 plus 8, which gives me 15, times x minus 7 minus 6, which would be a 1, which is positive 15, also greater than 0. So this one's less than 0. And the region we're going to shade is only when it's greater than 0. So this region that we tested here, we're not going to shade it. I just put an X through there indicating I checked it, and we're not going to shade that region. But the other regions are both, their test points showed bigger than 0, so we shade those entire regions. Just like that. That's the solution graphed. So written in interval form, we would write negative infinity up to negative 8, union for the second interval, 6 to infinity. So this is the compound answer. We wrote the solution in two different ways. All right, well, let's do a problem with a similar instruction. We're going to solve the rational inequality, where we have a polynomial over a polynomial, and we'll express the solution as we did before on this real line and then using intervals as well. Well, it's very similar to the previous in that we need to get our boundary points, but in this time we're going to solve the numerator, set it equal to 0, and solve setting the denominator equal to 0, and that gives us the boundary points. So the numerator, 3x plus 8 equals 0, means that 3x equals negative 8, and x equals negative 8 over 3. That's one boundary point. Second boundary point, 2x minus 1 equals 0, means that 2x equals 1, and x equals 1/2. That's the second boundary point. So we have, I'll put 1/2 right here, and I'll put negative 8 over 3 here. And I'll wait to fill in any of these boundary points with solid circles till the end. All right, so let's see. Let's pick a test point. What's a number? This is negative 2 2/3. So let's go to negative 3. Test points. Negative 3. And then in between them I could use 0. And a test point to the right of 1/2 I could use 1. And again, as before, I'm going to call this my function f of x. So now I need to get f of negative 3, f of 0, and f of 1. And I want to know if it's less than 0 or greater than 0. If it's less than 0, I'm going to shade the region. If it's not, I will not shade the region. So let's do the easy one first. F of 0 would give me 8 over negative 1. Negative 8. That's less than 0. F of negative 3 will give me a 3 times negative 3 plus 8 over 2 times negative 3 minus 1. That looks like negative 9 plus 8, which is negative 1. The denominator looks like negative 6 minus 1, which is negative 7. That's positive, right? Negative over negative is positive, so that's positive 1/7. Maybe I'll squeeze that in there. 1/7 is bigger than 0. F of 1 is going to give us 3 plus 8 on top, and 2 minus 1 on the bottom. That's 11 over 1, which is 11, and that's greater than 0. So we're going to shade the regions that are less than 0. So not this region, not the region containing the test point negative 3, not the region containing the test point 1, but the region containing the 0. So we're going to shade everything in the middle. All right, so we're almost done. I just noticed up above, no big deal, but I should have written the interval form up here in the blank, like that. And so for this, number 7, I'm going to write an interval form right here. But before we do that, let's figure out if we fill in the circles. Remember, it's less than or equal, but the denominator, 2x minus 1, we got the boundary point 1/2. If you plug in 1/2 into that denominator, you're going to get a 0. 2 times 1/2 is 1, minus 1 gives you 0. This needs to remain an open circle. But the other one would give you a 0 in the numerator, which just means the whole fraction is equal to 0, so we shade it. 0 is less than or equal to 0. This one is shaded, this one is not. You don't need to worry about that with polynomials. With polynomials, greater than you'll use, or less than, you'll do open circles. Greater than or equal, less than or equal, you'll shade the circles in. With these rational functions, you have to determine any x values that gave you a 0 in the denominator are definitely going to be open circles. And as long as the equal sign is included, then whatever gives you the numerator as a 0, negative 8/3 in this case, will be a filled-in circle. So the interval is negative 8/3 with a square bracket to 1/2 with a rounded bracket.